Hello, I'm Filipe Brandão from AMPL, and I'm here to present solver interface with callbacks in Python for Gurobi and CPLEX. I'm going to be using generic callbacks that work with both solvers without having to change anything in the code. I will start by introducing AMPL really quickly, then I'm going to show how it can be used from Python using our Python API, and then I'm going to present the callbacks. So, what is AMPL? AMPL is a mathematical programming language. It is a language designed just to express optimization problems. It works with multiple solvers, and you can easily switch from one solver to another without having to change anything in your model. It is quite natural and easy to learn. I'm going to show you a few examples, and after that you should be able to already start writing your own models. And it is really efficient to deal with huge problem sizes. So sometimes, especially in Python, people struggle after a certain size just to instantiate the problem object. In here, that problem usually does not happen because you are just, from Python, you are just sending data to AMPL, and then AMPL takes care of doing the expansion really fast because it was optimized just to do that by design. Let's see a simple example so that you can see the main entities in AMPL. There are sets, there are parameters, variables, objectives, and constraints. The parameters can have conditions, non-negative, greater than that parameter, a parameter indexed by two sets, a variable with bounds. So this is a diet problem. In here, we want to minimize the total cost of a diet while satisfying some nutritional constraints. For each nutrient, we want that the total amount of nutrients across the foods that we buy must be between a minimum and a maximum. And we want to minimize the total cost paid by the food bought. Now, how can we use this for Python? Easily. AmplePy is our Python API. You can install it with pip install AmplePy. With AMPL, here we are instantiating an AMPL session. We are reading a model file, the one from the previous slide. In this case, I'm loading the data from a data file, but I can also load the data directly from Python. I'm going to show you it next. Then I specify the solver, Gurobi, CPLEX, CBC, any solver that you want to use, solve, and then retrieve the solution. And in this case, I'm retrieving the solution as a pandas data frame. I can also use pandas data frame to send data to AMPL. So it is quite well integrated with the Python ecosystem. In here, I'm sending data. I'm using just Python lists, but I could also be using Python dictionaries, pandas data frame, NumPy matrices, and so on. Now, the diet problem is not the problem that needs callbacks. You don't need any callback for it. But there are problems that you cannot do much without them. TSP is one of these problems. And it is a quite simple problem to describe. You have a set of vertices, and you just want to find a tour that goes through every single vertex once, and that also minimizes the total distance traveled. This is an invalid solution with many subtours. This is a solution with a single tour, and this solution is in fact an optimal solution for this TSP instance with 280 nodes. Now, how can we solve this? Here is a quick possibility. Using the Python API, I'm instantiating the model directly in an eval statement. Parameter n, which will be the number of vertices from 1 to n. The arcs, in this case, there will be two arcs between each pair of nodes, one in each direction. It will be an asymmetric formulation because of these MTC constraints. The cost of each arc, which is the distance. A variable for each arc, which a binary variable that will be 1 if the arc is used and 0 otherwise. And we want to minimize the total tour length. So the sum across all arcs of the cost of the arc, the distance, times the binary variable that will be 0 or 1, depending on whether the arc is used or not. And other than this, we need to enter in each node once. Each node needs to be visited, and we also need to leave each node once. And with this constraint, we can ensure that there will be no subtours. Loading the data, okay, we have this function that returns the number of vertices and the dictionary with the distance between each pair of vertices. And we assign it like this. What happens if we try to solve this? This happens. So if we try to solve this problem, any MIP solver is going to struggle a lot. Even with 280 nodes, the MIP solver will already struggle. But you can still use this MTZ constraint up to like 50 nodes. It can still work, and also depending on the instance. Some instances are easier than the others. Okay, but I showed an optimal solution, so it should be possible to find it, right? And to do that, we are going to need callbacks. This callback is not going to help, but is just to show how can you use callbacks. AMPL Gurobi is the library for the Gurobi callbacks. You can install it with pip install AMPL Gurobi. And I'm going to use a generic callback. So I can switch this by AMPL _ CPLEX and the code will work just fine. So in constructor, we are going to have a variable to store a member to store the number of nodes. And the callback, this is what you always need to define in your class. The method run, which is the method that is invoked by the solver. And in this method, you can use this get AMPL where to get the generic information about where you are in the solve process. If you are in a message, so something that the solver just wants to output, you can output it and just add this to the beginning, in this case. If you are in a MIP node, you want to count MIP node and show MIP node count. And if you are in a MIP solution, you want, for instance, to just display the solution. This is a really basic use case. Does not help solving. As you can see here, you just have additional output, MIP solution, the character in the beginning of the lines and so on. And how can we use that callback? So we have the AMPL session. We export the model, in this case, Gurobi. We want a Gurobi model object. So M is going to be a Gurobi model object. Instantiate the callback. We set in model object that we want to use that callback. And we optimize. Then we check the status to see if the solution is optimal. And if the solution is optimal, we import the solution back into the AMPL session. And after that, we can do whatever we want to do in AMPL to process the solution, retrieve the solution, return the solution in a pandas data frame, whatever you might want to do after that. But we did not help it solve. Now, how can we solve that problem? Let's see a different formulation that will also help to show additional AMPL syntax. We are going to have an ordered set in this case, and we are going to have parameters for the coordinates. And instead of having arcs between nodes, we are going to have edges. So it will not be a directed graph anymore because we don't have MTZ constraints. And we have I nodes, J in nodes for every pair if the order I is smaller than J. So if I appears before J in this ordered set nodes. Distance, we are calculating this parameter distance automatically. So using square root. Also to show the syntax. And in here we declare the variables. Just like before, we have one variable for each, in this case for each edge, a binary variable that will be 1 if it is used, 0 otherwise. We want to minimize the tour length, just like before. And we need to visit every node. And in this case, we don't know if we are entering or leaving. We just know that each node needs to be in at least 2 edges. So at least 2 edges that will be at 1 need to be touching a node so that it is part of the tour. In here, we are not imposing subtour elimination. So how can we do it? We do it with a callback. So instead of putting the subtour in the model, like for instance, using MTZ constraints, we do it like this. And I'm also going to show another thing here. So the method run that we always need to define, we are in a class, right? So we can take advantage of this and organize our code better. So we can get AMPL where, if it is a MIPSOL, we invoke the method MIPSOL, and we can divide. If you have multiple functionalities in the same callback, you can organize the code and divide it into multiple methods like this. What are we going to do in MIPSOL? If we have a MIP solution, we want to check the get solution vector. So we want to obtain the current solution. And we use a unified data structure to identify if there is more than one group. Like I showed before in that TSP invalid TSP solution, there were multiple subtours. So if at the end, if we have multiple groups, we have an invalid solution and we need to add cuts. But if we have just one group, so everything is connected, then we have a valid solution. If we have multiple groups, what happens? We need to add a cut. So let's say we have a subgroup with 3 nodes. And in this subgroup with 3 nodes, we cannot have more than 2 edges with a variable at 1. So the maximum, the sum across all the edges between nodes in the group must be smaller or equal than the size of the group minus 1. Another alternative will be for edges between nodes in the group and outside, at least we will need at least 2. Will be another way to also enforce subtour elimination. And what happens when we use this? Okay, and first, how can we use this? In this case, we are going to use CPLEX, export CPLEX model, enable lazy constraints because we are using lazy constraints to exclude the solutions, instantiate the callback, set the callback that we want to use in the model object, optimize, check if the solution is optimal. If it is optimal, import solution and display the total length. Okay, in here I'm not showing, but this at the end we are finding an optimal solution. But let's see an interactive example, which is better. So here we have a Jupyter notebook where we show these cuts being used, and we also show the evolution, like the solutions that are found over time, the cuts that are being added. So you can see lots of subtours that we are excluding. So we get solutions every time we get a solution, we add the cuts. You see here the prints about the cuts being added. A solution getting better, but still with a subtour there. Other subtours. And here it is the optimal solution that I showed in the beginning. And the time that it took slightly over 10 seconds already, including the time to generate these images. And this was with Gurobi. And I'm going to, so the same code, if we use the generic callback, I'm going to show you where we have the callback. Here we have the model that I showed in the slide. And the generic callback is here. So this is the callback, and it also has the code to plot the subtours and so on. But similar in here, I use the other type of subtour elimination cut. So for every edge between a node inside the subtour and outside, we need to have at least 2 so that we are exiting the subtour and preventing it to exist. And that's it. So you see, this is a generic callback. Switch to CPLEX, use callbacks and plot subtours. I'm going to run. Where is it? Okay, here it is. We are in solve process, really bad solutions. Proving, but with subtours, we are excluding every time we find a solution. With subtours, we calculate them and we add the cuts. And here it is. We found the optimal solution again, the same distance as before. And without changing anything in the code other than this line here, where I specified the solver that I want to use. So to conclude, even though this presentation was focused in Python, we also have solver libraries with callbacks for other languages. For instance, right now we have for C++, which is the language underneath this Python library, and also C#. And we provide them to work, the generic callbacks that I showed, to work with multiple solvers. And we also have solver-specific interfaces if you really want to solver-specific functionalities. Even though we try to support pretty much everything in the generic callbacks, you might want to use something that is really specific, and we are not preventing you to use it. You can use it. You just lose the advantage of being able to switch from one solver to another easily. And here you can see how the project is structured, the Gurobi callbacks, express callbacks, CPLEX callbacks. Even though I did not show the express callbacks, we also have them, and the generic callbacks. And this is what available in every single callback. Finally, so to install these solver libraries, they are still in beta, but you can already install them, use them, and please use them and ask for feedback. We want to be able to support everything that people need, and your feedback is really important for that. You can install the one for Gurobi with pip install AMPL_Gurobi, and one for CPLEX pip install AMPL_CPLEX. Last but not least, all these interfaces are open source, so you can find them here in this GitHub repository. And if you want to contribute, feel free to contribute, or just open issues if you need any help or if you found any issue. The documentation is here in ampls.readdocs.io. And in case you are not familiar with our Python API, you can find the documentation in amplpy.readdocs.io. Thank you very much for your attention.